All right, hello, and thank you so much for the opportunity to speak at this meeting. I'm really excited to be here and share with you some of the work that I've been doing in my lab at the University of Waterloo. So I should just say that with my background, I'm a kinesiologist. So I'm infiltrating vision science just a little bit here. And I do have a connection, a second degree connection, I guess, to the Smith-Kettlewell Institute. My PhD supervisor, Marty Steinbach, was a fellow here. So he always came back from the annual meetings and talked about it extensively, and he had lots of fun here. So I'm super excited to be here and talk about the research that I'm doing. All right, so in this talk, I will highlight how binocular vision facilitates the development of visual motor control and the performance of fine motor skills. So just a quick overview. I will start with a quick overview of binocular vision and upper limb movement control. And I will spend a lot of my talk discussing the literature that we currently have on the contribution of ocular convergence and stereopsis to visual motor control and how the system is affected by amblyopia. And hopefully I will have some to talk about the clinical implications that this work may have. I suspect that a lot of people would agree vision is a key sensory input for motor skill learning and performance. Babies begin to reach towards visual objects and toys between 3 to 4 months of age. And in that first few months and years, there's such a tremendous amount of development in their visual motor control. Children engage in so many different activities to build their foundational motor skills. And this is important because there is a correlation and an association between fine motor skills and later academic performance. And we know visual motor skills are important throughout our lives. If you think about it, a lot of the things you did today, grabbing your keys, your coffee, and many other things, rely on visual motor control. There are some professions that require very high level of visual motor control, for example, surgical training. And as was already mentioned today, vision develops rapidly in the first few months and years after birth. So this is an improvement in acuity, and binocularity in terms of stereopsis emerges between 2 to 4 months of age. All right, there is a condition that affects the typical development, and that's amblyopia. So amblyopia is a neurodevelopmental visual disorder, quite frequent, affecting 3 to 4% of the population. And it's often associated with 3 conditions also mentioned today. So strabismus, anisometropia, and image degradation due to infantile cataracts. The diagnosis of amblyopia is usually made based on visual acuity. So when we see a difference of at least 2 lines between the 2 eyes, that usually signifies amblyopia. The most important thing to remember here is that there's nothing wrong with the eye or the retina per se. The problem starts at the level of the cortex. So amblyopia is a cortical visual disorder characterized by reduced acuity and binocularity. And if you have something that affects the brain in those early visual areas, the primary visual cortex, you might expect that there would be effects downstream on higher level visual areas. And my specific interest is in the dorsal stream. So dorsal stream that's projecting to the parietal cortex, that area of the brain is involved in visual motor control. So just a quick overview of binocular vision. This is my way of simplifying things a lot. So this is presented here in the form of a triangle. And at the base of the triangle, we have simultaneous perception. There's a lot of research showing improvements in performance when the 2 eyes are working and open. We have improvements in performance on acuity tasks, contrast sensitivity, motion thresholds. In the context of motor control, there's also improvement in reaction time, so we can respond quicker. And this may be due to binocular summation. At the next level here, we have fusion. This has 2 components, sensory and motor. Motor fusion refers to vergence eye movements, and this can provide a signal about absolute depth. So the muscular effort that's associated with keeping the eyes converging on a particular object provides the system with information about where is the object in relation to the body. The sensory aspect of fusion refers to stereopsis. So here, this is a signal that tells us a little bit more about relative depth. So in my image here, you can look at the object, and there is a depth component there. So relative depth information helps us with perhaps grasping. In the pinnacle here, I have fine stereo acuity. Stereo acuity, generally speaking, can range between 3,000 arc seconds, so pretty gross, to less than 10 arc seconds. And the question the question that I'm interested in is, what is the effect of reduced stereo on visual motor performance? Does it matter? Should we have clinical training or rehab to improve stereo acuity to such good thresholds here? All right, so I'll speak a little bit about the framework that I use for thinking about motor control. So if you think about very skillful movements, these are movements that are usually performed fast, accurately, and precisely. And the performance of such movements relies on two control processes: feed-forward control, which is involved in movement planning, and feedback control involved in the execution of the movement. We can dissect things a little bit because they're never that simple. So here I'm just going to dissect the parts of feed-forward control. In order to make movements, we first select the object that we are interested in. We need to localize that object in egocentric coordinates, and we need to encode the properties of such objects. All of that information would come from the visual system. The other part, the other input that we need is the position of the arm, and that would usually come from the somatosensory system. So combining this information, we get a motor command, which is sent to the arm muscles, and we have a movement. So notice here that the green parts of my framework represent feed-forward control, and the pink is feedback execution. And the first part of the arm trajectory reflects feed-forward control. That's important to remember. And one way to get some insight into these control processes is to look at movement kinematics. So we can use a high-speed motion capture system, put a marker on the finger or the arm, and record the position of the limb as it is engaged in the movement. So here I plotted limb velocity for a typical prehension movement. So the movement starts, and this part up to peak velocity is referred to as impulse control. So this is reflective of that feed-forward planning. And after peak velocity, you can see the limb is decelerating. So as we are slowing down, there's a lot of opportunity then to use feedback to fine-tune the movement and correct for any errors that might have occurred during programming or the earlier parts of the movement. As soon as we touch the object, there's also somatosensory feedback, which can help with the grasping part. All right, so the question is, how does binocular vision help with these processes? I'll start with vergence, and there's literature that shows that vergence is important for movement planning. This may not be surprising, as you can see, the first part of planning involves localization. So localizing this object, vergence can help with that. And the evidence here comes from a very old study by Ono and Weber. In this study, they asked participants to point to a visual target under different viewing conditions. One of them was monocular. And with monocular viewing, people usually experience phoria, which changes the posture of the eyes and affects the localization process. So in this study, they showed a correlation between phoria magnitude and endpoint error. One of my students was interested in the dynamics of this response. So what I plotted here is the limb trajectory on the y-axis across that very early part of the acceleration interval. The black line is binocular viewing, and the two colors, the green and the red, represent the two monocular viewing conditions. And here again, during this very early part of the trajectory, we can see a distinct and a significant deviation. But in this particular study, participants received visual feedback during the movement. So that error was corrected by the time they got to peak velocity. So the system, again, has a way of correcting these errors. All right, so next I'll move on to stereopsis. And the literature here suggests that this is important for grasp execution. The figures that I'm gonna show you here come from Grant and Melmoth, who did seminal studies with people with amblyopia. They asked them to reach and grasp an object. So plotted here are grasping errors on the Y. And this is all during binocular viewing. The different colored bars here are different groups of people. So white is the control participants. They made less than 10% errors. And people with amblyopia, mild and moderate, had about 15% errors. And people with the greatest disruption to their vision and binocular vision had more than about 3 times errors, so 30% errors. In another study, they also showed a correlation between grasp duration and stereo acuity. So shown here is the idea that people with better stereopsis also have more efficient, shorter grasp duration. So this is data from patients, which gives us some indication that stereo is important for prehension, but it doesn't really tell us why. So in my lab, one of my students was interested in following this question, and we hypothesized that stereopsis contributes to the predictive control of grasping. So again, vision is important for encoding the properties of the target, and stereopsis could play a role here. To look at the predictive control, we leaned on the literature. And there's a lot of literature in motor control, which shows that grasp forces are programmed predictively based on the expected properties of this object. So shown here is a pretty standard figure from a textbook, which shows you load and grip forces. And you can see here that they are applied quite quickly after contacting the object, and they are scaled to the object's weight. So again, supporting the idea of predictive control. In our study, we manipulated stereopsis by placing a convex Laplace lens in front of one eye, and they're reducing stereopsis to about 200 arc seconds and more than 400 arc seconds. Our main outcome measure was to look at force magnitude, which is plotted here on the left. So grasp force magnitude very early, 50 milliseconds after contacting the object. And the black bar here is binocular viewing, that force was significantly higher in comparison to the stereo reduced conditions and to the monocular condition. The second figure shows time to peak force. And again, you can see how much more efficient this movement is with binocular viewing, and it's taking quite a bit longer during the other conditions. So this study supports the idea that stereopsis may be important for the predictive control of prehension. So just to summarize very quickly in the context of this multiple processes model of limb control, Vergence has a role for impulse control. So this is for programming the initial direction and distance. And stereopsis has a bigger role in the latter part of the movement when the hand is approaching the object. So this is limb target control. And in grasping itself, so in generating appropriate amount of force to grasp the object most efficiently. All right, so next I just want to move on to visual motor development. So the questions that we are interested in is how does binocular vision facilitate the development of visual motor control in typically developing children? And how is the system affected by amblyopia and strabismus, so impairments in binocular vision? So I'll start with sharing the rationale for the task that we have implemented in my research. So one of our first studies compared performance on 2 tasks, bead threading, which is on the left, and the pegboard, which is on the right here. Both of these tasks seem similar on the surface. Both require reaching, grasping, and precision placement. And the performance on these tasks is plotted here in terms of movement time on the Y across the different ages, so from 5 years old to adulthood. And you can see a nice developmental trajectory. This is for binocular viewing. I'll add the monocular viewing condition here. And we had a very striking difference between the tasks. It seemed that the bead threading task was much more affected by the lack of binocular input. So performance was disrupted to a greater extent. And one reason that may account for this is that the bead threading task requires a lot more precision for both grasping and placement. So this is the task that we selected as a probe to further examine the role of binocular vision. And I'll show you next the kinematic signature for this task, starting with the video here. So here's the setup, and the red cursor here represents gaze location. So you can see that eyes and hand are precisely coordinated for the performance of this task. And this is fairly stereotypical. These are the data that we get from our system. So this is position of the eyes and the hand during the performance of the task. And here is the velocity profile, which is quite useful for getting the outcome measures that we are interested in. So here we get the peak velocity of each reaching movement, which is reflective mostly of the feed forward control. We can look at the duration of each reaching movement, and we can then divide it into those two phases for impulse control and limb target control, and the two phases involved in object manipulation. So we can define these things objectively based on the velocity criteria. So I'll show you one figure here, which illustrates the developmental trajectory for one of these outcome measures. This is grasp duration plotted here on the Y across ages from 4 to 16 years old. These are all typically developing children. So you can see here that performance stabilizes or matures around 10 years of age. This is quite typical for the other outcome measures in this study. And one striking thing you can notice here is the amount of variability that we see in typical development. And the question that we were interested in is whether some of this variability could be explained by binocular vision. So there was another study conducted to address this question with 60 typically developing children. And the punchline is that we did find an association between different aspects of binocular vision and better control of distinct phases of prehension. We found a correlation between horizontal fusional reserves and peak velocity. Stereo acuity explained about 16% of variance in grasp duration, and accommodative ability explained about 13% of variance in placement duration. So even in typically developing children, we see a range across of values in these outcome measures, and they do help with visual motor control. So the next slide here is going to show you some results from children with amblyopia. This was a pretty small study, which was disrupted by COVID. So again, the task here is the same. The outcome measures are listed at the bottom of the slide. And what I plotted here is standardized scores on the Y. So 0 is the mean of age and gender matched controls, plus minus 1 are the standard deviations. And it's a busy slide with all the symbols here representing performance across the different children with amblyopia. Overall, there was no difference between the mean of the patients and controls for reach-related measures, things like peak velocity or reach duration. We did find a significantly poorer performance for children with amblyopia on the manipulation parts of the task. So grasp duration and thread duration were both longer. And there was an association between stereo acuity and grasp duration in the sample as well. All right, so if anyone is interested in hearing a little bit more about this research and eye-hand coordination, we do have a poster that will be presented later on by Susanna. So just to summarize, what the literature right now, I think, is highlighting is that deficits in binocular viewing are more evident for actions and motor behaviors that require skill, where there's a requirement for both speed and accuracy. I think what we are seeing here is also a reduced ability to use vision for planning. So vision is a system that allows us to see things ahead of the time. And we can plan how we are going to make these movements and the forces that we need to exert to make these movements efficiently. So I think that all of these feed-forward planning processes that rely on vision, they will be impacted in people who have amblyopia. And what we are going to see is either a deficit or some sort of compensatory adaptation, which we know the system is really good at. And I think that at the end of the day, normal binocular vision is really important for calibrating the system for optimal performance. So this interaction between feed forward and feedback control is really dynamic, And with better vision, we are just better calibrated and more efficient and skilled at different types of motor behaviors. So just ending with the implications, I think overall, this research could be applied towards developing better assessment tools. So right now in the world of clinical assessments of fine motor skills, people are using a stopwatch, a paper, and a pencil. And that's how we assess fine motor skills. With the technology that's emerging, kinematics, and eye and head tracking, I think we can do a lot better. Instead of testing just very crudely to identify that a child has a problem, we could use the technology to determine what is the problem. We can maybe say, well, did they look at the right thing at the right time? Is it a problem with eye-hand coordination, or is it a problem with the way they are executing the movement? So I think there's a lot of opportunity here to start translating this research into those more applied settings. Of course, this is going to be extremely challenging. And I'm just going to end with a video here of a task that I'm very excited about. This is showing you basically bead threading. If you think about it, people are grasping beads and putting them on the pegs. But it's embedded in another task, the Tower of London. So the top the 3 beads at the top are the model, and participants have to plan. So they solve how to move the beads in the bottom to make the model. So here's an example of a task where we could probe sort of higher level vision and how it is used to guide actions in contexts that are more reminiscent of what we do in everyday life. We don't just reach and stop. We do complex things, and we do not assess these things at that level. So I think that's where the future lies. And with that, I just want to say thank you to all the collaborators and students who have worked on this research and the funding agencies. And thank you so much for listening. I hope I didn't go too far into motor control in this meeting.
Thank you for a terrific talk. We have time for a few questions for Ewa.
So you, in your first part, you identified a relationship between stereopsis and grasp force. My naive view about grasping is that grasp force should be influenced by your assessment of what that object is made of, materials, what I need. So how gives hypothesis about why or how stereopsis is impacting that and why?
Yeah, that's a very good question. So I think that stereopsis, the main input there is about relative depth. So how far is the object extending in depth? So maybe how big this object is, and that will definitely impact the force with which you are, going to grasp it. But I think what we are seeing here is with reduced stereopsis, there's more uncertainty in the system. There's visual noise in the system, and that is affecting the way you're going to be interacting with the object. So maybe what we are seeing here is just, more noise because the stereo signal is reduce and things are not as usual, right? When you have this perturbation on the visual system, it's just maybe introducing uncertainty, and the way that the system deals with uncertainty is that by slowing down, by maybe not exerting as much force, because as soon as you touch it, you're going to get somatosensory feedback. So there's that interaction between vision and somatosensory information. And if vision is not so good, I'm going to rely more on somatosensory system. I'm going to touch it maybe more lightly, which is what we showed, and extend that somatosensory contribution, upweight that signal to compensate for my visual deficit.
Keeping the material that you can touch and randomizing the mass. And
yes,
adding noise that way, then you could do some interesting calculations.
Yeah, so we did a bit of an exploration in that as well. Yeah. In this particular study, all the objects that people were interacting with were a little bit different. We had different sizes, different textures, different colors. So people couldn't just form a motor plan in the first 5 trials and use it for the next 50. They had to really look and extract the relevant properties and code that to guide the movement. But yeah, I can't speak to the question that you have, manipulating the mass. We just didn't have enough in those trials.
There are a couple of questions in the chat. Let's see if I can read them. Okay, so this question from the chat, you showed that reach parameters were not that significant when compared to grasping. So what parameters do you feel is important in visuomotor in amblyopia? Is it the reaction time and precision?
Yes, so there are so many parameters that we can look at when looking at visual motor control, and specifically the kinematics of the movements. I literally get 60. Only some of them are useful, and there's a lot of correlation between things. So generally speaking, with amblyopia and strabismus, we do see longer reaction times on some tasks, but not all. It may be different in development, and that's what we are showing on our poster later on. I think, with amblyopia, it's a heterogeneous disorder to begin with, right? We have people with niechwiej-Szwedo and strabismus and mixed and maybe cataracts. So I think that, the clinical history of people might influence where they are having difficulties, right? So generally speaking, in our studies that examine relatively simple things, we didn't find a lot of effects on the reach. But there is a subset of kids that might be affected on that as well. So, in my figure, I showed you all the symbols. Overall, on mean for that cohort, we didn't see a difference for reach duration or peak velocity. But there are some kids that are doing worse than the controls on those. So there's a lot of heterogeneity, and I think it's really hard to just say, look at this parameter or another parameter. I think there's a lot of work that needs to still be done to characterize how the different clinical characteristics of children could potentially impact different aspects of visual motor behavior, and how that is reflected in those outcome measures that we choose to analyze.
Here's a question over here.
Thank you. Just a quick comment and also a question. I completely agree with you when you say that we can do better. The technology exists to follow the eyes, to follow the hands. We should be definitely doing a deeper dive. So I congratulate you on that effort. We're doing a similar study in another developmental condition. What we find is that when we do a visual haptic task, the eyes are always one step ahead of the hand and neurotypicals. I'm wondering, in your population, are you seeing that gap collapsing, for example? And are the eyes really where the hands always are? What have you noticed looking at hand and eye kinematics in amblyopia?
Yeah, that's an excellent question. It is somewhat task dependent, right? So when we look at the eye-hand coordination to an external stimulus, for example, visual target or auditory target, you're going to get that 100 millisecond difference between the eyes and the hand. It's been shown there isn't a huge change in amblyopia, at least in adults, just maybe a few milliseconds, which may be significant and may be impacting their life. I don't know. But there are other aspects of eye-hand coordination. So once you get going on a task, that 100 milliseconds is no longer there. There's a very different pattern that we're seeing on the bead threading task, for example. There's actually zero delay. The eyes and the hands go approximately at the same time for adults, and there's a developmental trend that happens as well. In amblyopia, again, Susanna's going to talk a little bit later on the poster. There are interesting changes that may happen, and you're right, the eyes precede the hand. maybe you've noticed on the video that I was showing, right? So yeah, and that's a very interesting finding in the literature. Sometimes this gap between the eyes and the hand is about a second. And it was very hard for me to believe that till I saw my data that, yeah, it's there. And a lot of this is task dependent. So mapping this out will require a lot of work in typical, probably individuals and in different neurodevelopmental disorders as well. I think it's a huge field that should be explored.
Thank you. You also talked about calibration and the importance, and I'm just struck by the fact that Preeti has shown that patients with low vision who lose vision in one eye more than the other and lose binocularity also have problems, particularly in a peg placement task where they have to rely on binocular vision. And I wonder if somebody with amblyopia when they're 3, 2, whether they learn to calibrate and show less severe abnormalities compared to somebody who just recently loses binocularity, and whether that's due to calibration.
Yes, I think so. I think the age matters a lot. There's a lot of neuroplasticity that happens early on, a lot more than happens later. So neuroplasticity, of course, happens throughout our lives, but it's the potential is probably greater in someone who is younger. So even the reweighting of how you're going to rely on vision versus some other sensory information during visual motor tasks. Yes, age matters a lot. I don't know if I answered your question.
Yeah. One more question, and I think then we'll go on to the general discussion. Thanks.
It's a little bit to what you just said. It's kind of broad and naive. So if stereopsis contributes to your feed-forward planning, this plan, your internal model, also requires proprioceptive input, and that develops a bit later than vision. So I was wondering if you think that if you have a stereo deficiency as you're growing older, is this going to delay the elaboration of your body schema?
Well, thank you. That's a really tough question. Is it on? Okay. All right. Okay. Yep. Thank you for the question. It's a tough one. This is about multi-sensory integration and the body schema to some extent, I guess. And I'm not sure I have an answer for this at this point. There's a lot of interaction that happens, right, between the somatosensory system and the visual system in the context of visual motor control. The way that I think about it is that any task you do is multisensory, right? Like just by definition, you're using vision to plan. You need to know where your body is. You have to put these things together somehow to interact with this dynamic environment. So it's really complex. So your question is about a delay in development of the proprioceptive sort of system and somatosensory system and the body schema in amblyopia, or yeah. So I guess I would, maybe it's the opposite. Maybe it sort of develops sooner because you have to rely on the signal more. But I don't know the developmental trajectory of the somatosensory system or the proprioceptive system. And yeah, I'm sorry, I can't answer the question very well for you.
Thank you, Eva, for a fabulous talk. We'll go on to the general discussion. There are some questions more for Eva in the chat, but we'll get to them shortly. So.